Right, so today I'm going to be telling you about, well, path sampling, the methodology, and talking about OpenPathSampling, the software that I've helped write. This is, well, this is going to be set up so that we'll mostly have just a talk for the first half of this. This is actually based on material that I use. Alan, am I on? Okay. Just checking that my mic's working. This is based on material that I use for a master's course that I've given a couple of times on biomolecular simulation, and so this is aimed first off at that level. It's also tested, so it's been used before. We know it should be feasible to get through it. That also means that there are a few parts where there's a lot of math, and I'm going to go pretty quickly through the more math-heavy parts. You'll have access to the slides, so it'll be useful for you in the future if you want to go back to this, but I don't want to put you to sleep with all that math. So this is basically the outline of what's going to happen. We're going to talk about rare events in general. What is a rare event? Why do they matter? Transition path sampling, which is sort of the core method behind all of this. And a lot of stuff in here with the derivation of the shooting move and variants of the shooting move in particular. That's where there's a lot of math that I'm just going to go over a little quickly. If you want to do these things, if you ever want to actually use these methods, you need to worry about some practical things. And so I'm going to talk about that. Now, I'm going to give some motivation at the beginning, but we're really going to dive into the details of what results we get from path sampling, what they mean, and how to interpret that here. And I'll give you a couple of examples, mainly one that I'll dive into detail on that we're currently writing a paper about where we've used transition path sampling. Then I'll go to transition interface sampling, which is a very closely related method that's used to calculate rates and free energies. And at the end, we'll talk about OpenPath sampling, and then we'll have the break, and then we'll come back and we'll do the tutorial, the hands-on. Start out with rare events, if it will advance my slide. So there are a lot of equations I said later on the slide, but there's one equation that is more important than all the others. It's this one. I think we're all familiar with my friend Boltzmann here. And I always like to say that Boltzmann is beautiful, but Boltzmann is terrible. And the reason that Boltzmann is beautiful, you can see with these two strands of DNA. They look pretty much the same to you, don't they? There's little differences if you look carefully. But to this protein, they are completely different. This protein is much more likely to go to one of them than it is to go to the other, to attach to one than to the other. Which side is it more likely to attach to? Well, unless you've seen this talk before, you've probably got about a 50% chance of getting it right. And that's despite the fact that you're smart people. And you can also look at this. We've got like pretty colors, so you can tell what all the atoms are, which ones are which. The protein doesn't have that. It doesn't get to look at pretty colors. You get to look at this from a distance and really see the whole picture. The protein doesn't have that. So why is it that the protein knows something like 100,000 times to 1 that it goes to the DNA strand on the right? Because of Boltzmann. Because the differences that you see that are very small, that lead to linear changes in the energy, get magnified to be an exponential difference in the probabilities. And that's beautiful. Why is that beautiful? This protein is a transcription factor. It's a repressor protein. It attaches to the DNA and prevents DNA after that section from being expressed. It has to be very specific in what it attaches to and where it connects to the DNA. Because if it wasn't, I mean, its specificity is basically the reason that we're all alive. That's necessary for this thing to do its job. It has to be very specific. If these things didn't do their job, we'd all be we would never be alive in the first place. So that's a beautiful thing. Boltzmann's also a terrible thing. And that's because when you are a simulator, as we all are, someone who wants to do classical molecular dynamics, Boltzmann makes our life kind of miserable, at least if you have something like this, where we have a barrier that's separating, let's call them reactants and products. And you all know that we have a delta G of reaction, that there's something called the transition state. There's this delta G at the transition. And the higher that barrier is, the higher that delta G double dagger is, the less likely the transition is to occur spontaneously, or the longer you have to wait to see the transition occur. So let's just do a real simulation on this. So just a one-dimensional thing. It's going. It accumulates a little bit of red to say where it's been before. That's basically the free energy popping up in the color of red. I really want to see this transition happen. I want to understand what happens during this transition. I'm still waiting. At some point, it really will go over to the other side, but wait, this is actual MD. This is a trajectory from real MD that I did. Yeah, MD on this surface. Still waiting. There, finally. Okay, it transitioned, and it happened really fast, didn't it? So it switched over really fast. If I want to know what's happening during that transition, which is what I'm interested in, my question is, what happens? What's the mechanism of this transition? I mean, one-dimensional, not very interesting mechanism, but in general, what's happening during these transitions? I have to wait a really long time to figure that out. And the other thing is, I told you that the amount of red at each point is going to be proportional to the free energy, or related to the free energy at least. If that were true, then I should see the same thing at a line here. But this and this are not the same. Why aren't they the same? Because the simulation is nowhere near converged, right? I've only seen one transition in one direction. So if I want to get this kind of information, I'm going to have to wait forever. And that's fundamentally the problem of rare events. What is it that makes an event rare? It's a separation of timescales. We have a timescale that we need to do our dynamics versus the frequency of the event, how long it takes for the event to occur on average. And I think, there we go. Biomolecular systems, which is where I've done most of my work, the time you would have to wait to see something happen, once per millisecond is not unreasonable, once per microsecond maybe if you've got a faster thing, once per 100 seconds if you're looking at drug unbinding. Time step is going to be on the order of a femtosecond. So if it's once per millisecond, you need to wait 10 to the 12th time steps to see that happen one time. So if these events are so rare, who cares about them anyway? This is the problem of naming the field rare events. People never understand why they're important. Everyone cares about rare events. Whether you're interested in sort of the biological things like I do with sort of conformational changes and folding and binding events, enzyme reactions, or whether you're interested in crystallization, self-assembly, fluid dynamics like formation of micelles, and of course chemical reactions, catalysis reactions. Rare events are ubiquitous in the chemical sciences. The specific kinds of questions that I like to ask are things like these. So these are 3 things that had underway recently. One of them is about a specific transition in DNA that I thought was interesting, and you'll see some movies from that later on. Another one is about a cancer-causing protein, where we looked at the cancer-causing version and the wild type and said, can we learn something about why it is that the cancer-causing version causes cancer? I'll talk about that in more detail. Also, we're interested in how drugs unbind from their target site, binding and unbinding. This is really important because essentially the longer it stays in the target site, the more effective the drug is. And so this is something else that we've been looking at. So that's sort of the motivation. Why does anyone care about rare events? And I hope you all do now. Now I'm going to talk about the methodology. So this slide, again, you'll have access to all of the slides and such. This is just so you have, for future reference, some useful literature. The last review in particular, which was, they're due to write another one like that, but it's a book chapter. It's actually more like a book itself. It's about 100 pages long, but it's a phenomenal review, and I recommend starting with that if you can. So, problem of rare events. We've got to solve this. How can we get lots of these transitions? So I said that we need 10 to the 12th time steps to see one event that occurs once per millisecond. GPUs and other tools we have for high-performance computing are amazing. With a moderate-sized system on just a single GPU, you can do 100 nanoseconds a day. 100 nanoseconds a day is, if it's a femtosecond time step, that's what, 100 million time steps every day. 100 million force calculations done every day by your GPU. That is amazing. But if I need to see an event happen once per millisecond, that means I'm going to have to wait about 30 years to see that. Doesn't help me much yet. And that's to get one event. A single transition is not data. A single transition is nothing but an anecdote. We need to see lots of these events if we want to make any firm scientific conclusions about them. So what we're going to do is use path sampling, which what it does is it focuses in on these transition regions. Notice that what happens here is characteristic for these kinds of transitions. There's a very fast transition with a long waiting time. So the hops are relatively sudden. We're going to do a Monte Carlo in path space in order to show how this happens, in order to study these things. So that's why we're going to review Monte Carlo. I assume that everyone here has done Monte Carlo of some sort before, so I hope so. But just to remind you, typically when we do Monte Carlo, we are concerned about maintaining what's called detailed balance. And detailed balance is just this. You have the probability of being in the old state times the probability that you go from the old state to the new one, and you require that that be equal to the probability of being in the new state times the probability of moving from new to old. If you do this, you automatically guarantee that you preserve that distribution rho, and that's why we care about it. This is not the only way to make sure you preserve rho, but if this is satisfied, then you preserve rho. So the trick here is that then you'll split this transition probability pi into a generation probability and an acceptance probability. And you'll solve for the acceptance probability. Well, first you'll take the generation probability. The generation probability is based on your algorithm. So you break it down into little steps, and we'll see a lot of this coming later on. And you figure out what the probability of each step is, and then you solve for the acceptance probability. Now, the acceptance probability, there's not a unique solution for the acceptance probability. There are a couple of options, but the one that's most widely used is the Metropolis or Metropolis-Hastings acceptance rule, which says that you take the acceptance probability is the minimum of 1, because you can't have a probability greater than 1, times the ratio of the probabilities of the thermodynamic probabilities times the ratio of the generation probabilities. Important thing here is that this only requires ratios, because for a lot of these things, you can figure out what the relative probability of two things are, but getting the actual exact normalization is really hard. So that's the idea there. Just as an example, how we do this, let's make a really simple Monte Carlo simulation. I have a bunch of atoms. My generation probability, well, my algorithm is going to be I'm going to select an atom at random. So there's a probability that I selected that given atom. And then I'm going to move that atom some random distance or direction. So there's a probability of having made that specific move. And that is my old to new probability. I also have to figure out my new to old probability. But if I say that the probability of selecting the atom is the same, well, reasonable, and if making the sort of reverse move is the same, then these two probabilities will be the exact same thing in both directions. As a result, I can put this into the Metropolis rule, and this p-gen, which you can probably not see well because it's at the bottom, it cancels out, and you get that this is just the ratio of the probabilities of the states, which is what you probably remember as this being a e to the minus beta delta e, right? Something like that you've seen before. So that was Monte Carlo, just to remind you what you should know. Now let's move on to Monte Carlo in path space. So again, a bunch of notation. This is more for reference for if you come through the slides later. But the big thing is I use bold x's for a trajectory and italic x for a snapshot. And then what we called rho when it was thermodynamics, we use this capital script P. And yeah, the rest is all pretty straightforward. That's for the path ensemble probability is the capital script P. So again, here is the detailed balance for configurations. When we do this for trajectories, it looks like this. What's the difference? Not much. All I did is I turned the rho to a P and the italic x to a bold x. It's all the ideas are exactly the same as it is in regular configurational Monte Carlo. Now, I guess I've said we have here these ideas, but we need to figure out a way to calculate these things, right? We need an algorithm for this, and we need a path probability for that, because you know the thermodynamic probability because you've studied statistical mechanics. What's the probability of a trajectory? And so that's where we have to think about what a trajectory is. And a trajectory, as you all know, is a sequence of discrete time snapshots, right? We've discretized time when we do a molecular dynamics trajectory. And so the probability of generating that trajectory is proportional to, we've got a normalization factor, but other than that, the probability is the probability of being in the initial state times the probability that you went from the initial state to the next snapshot after that, times the probability of going from that snapshot to the next one, and so on until you get to the end of your trajectory. That's all it is. The initial probability just comes from your thermodynamic ensemble, and the details of how you move comes from your integrator. Fortunately, as we'll see, you usually don't need to worry about the details of the integrator. If under certain circumstances, the integrator will just cancel out, and we won't have to worry about it. The next thing then, so we've got a probability for a path, for a trajectory. Now, how do we focus in on that transition region? Remember, I had that transition region circled in red. How do we narrow in on that? And we're going to use these indicator functions to do it. So the idea is that you have an indicator that just returns 1 if you're in state A, that's HA. You have HB returns 1 if you're in state B. If you're not in that state, it returns 0. This little thing that says that the sum isn't equal to 1, that's because there are regions, so there's stuff that's in A, there's stuff that's in B, and there's stuff that is not in A and not in B either. So that no man's land in between is an important part of how path sampling works. And so we include that. What we will do then is put a restriction, make a restricted path ensemble. We put a restriction on all the trajectories. So this is taking the regular probability for all the trajectories that there could be. And we require that the trajectories start in state A and end in state B. If it started in A and ended in B, then there was a transition. And so this is how we create the transition path ensemble. Now we need an algorithm that will allow us to create new trajectories. And this is where we use what's called the shooting algorithm. And the idea here is we start from a trajectory. So just like in configurational Monte Carlo, you start from a list of positions, a configuration, and you modify that in some way. In path sampling, you start from a trajectory, and you modify that in some way. So what we're going to do is we're going to select a point from our trajectory frame, just like we selected an atom before. We select one of the frames of the trajectory. We'll call that frame tau, and we'll call it the shooting point. We will modify the velocities at that point. Maybe we completely randomize it. Maybe we just turn a few velocities to a different direction. And then we're going to run the dynamics forward and backward. And so if we've got time tau and we have a fixed length, we run backward to time 0 and forward to time L. And so we have to run dynamics forward and backward to create the new path. So again, we have this big mess here with all of these things. Let's talk a little bit about what we usually do, a few tricks to make this a little easier. Well, so again, we're gonna assume here that we have an equal probability, except for we don't take the two endpoints. We don't take 0, we don't take L, but we'll take anything else. So the probability of selecting any point is going to be 1 divided by L minus 1. We'll just assume that the modification we make is symmetric. If you completely randomize the velocities according to the Boltzmann distribution, that will be true. If you do one of these sort of turns of the velocity, you have to make sure that it does, in fact, switch back the other way with the same probability. But just for now, let's assume we've got that. Then the probability of making the forward segment is just the probability that we had from the integrator that you move forward. And I'm going to introduce a slightly different notation where we have a bar on the top to say that's the probability of making the backward trajectory. So going backward is just with the bar on the top. That basically means that you're running with your velocities reversed. In practice, doing this symmetric p modification is a little bit tricky when you have constraints, because keeping velocities correctly constrained to the manifold is a mess. But we'll also talk about how we get away from that problem in general for at least biomolecular systems, for large systems.
Sorry.
Yep.
You're assuming that if we change a little bit of the velocity, so at some point along the trajectory, we will definitely end up in P. And if we integrate back, we will definitely get there.
Not yet. Not yet. No. The assumption is that you can create a trajectory. You can create a trial trajectory, a trajectory that's of a given length, and that you certainly can. Just so as an aside here, there's something else that's going to become very important, and this relates to this p-bar thing I introduced, which is called microscopic reversibility. Microscopic reversibility is just like detailed balance. You'll see the equation looks just the same, except it's about the dynamics, not about the Monte Carlo move. So the rule here is that the probability of going from some state times the probability of doing the dynamic step in the forward direction is equal to the probability of being in that configuration times the probability of doing the dynamic step in the backward direction. In practice, most of your integrators, or many integrators, are reversible, and there's an argument that even if they aren't, they satisfy it to first order, which is supposed to be good enough. I'm not sure I think that's the best argument to make, but hey, people have made it. In general, if you can, you want to take an integrator that is reversible and also symplectic, because that just gives you better statistics. We'll use this later. This becomes really important later, so we'll come back to this idea of forward and backward propagation and microscopic reversibility. Okay, so now I'm going to figure out the acceptance probability for my move, and that is going to be just, again, this is Metropolis Hastings, so this is my probability in my ensembles. These are my probabilities of doing the forward and reverse move. I've broken that probability down into this horribly ugly mess that you can probably barely read from the back because it's got so much in it, but let me make it easier. First off, we said that we're going to use a symmetric modification of the shooting point, so that part of the ratio becomes 1. That already feels a lot better. Second, the selection for the shooting point selection probability is 1 over L, or 1 over L minus 1. 1 over L minus 1 divided by 1 over L minus 1 is going to be 1. So that part goes away. Now we've got it massively simplified. Life's a lot easier now. And I'll just take, I'm just going to take this thing and put it up here now, right? Because that's what I have. So on the next slide, that's just moved up there. And now I just need to think about how I'm going to use these things and cancel out some more stuff. So we know what the path probability is, right? We figured this out already, that this is our restricted path probability. This is the total path probability. This is the restriction part. I don't worry about the normalization factor because it's the same in numerator and denominator. This is where we use microscopic reversibility. So the trick here is that because of microscopic reversibility, I can take this x0, this row of x0, and I can take the row of x0 and p of x0 to x1 and turn that into row of x1 and p bar of x1 back to x0, the reverse dynamics, right? I take this and replace it with this by taking pieces of that out. And if I moved it from x0 to x1 and the reverse back one step, I can do it again. Move it to x1, row of x1, and now we have 2 reverse steps. I can keep doing that all the way up to tau, my shooting point. And when I do that, I end up with this. So this thing turns into this. And if I look at what I have here and here, those products are exactly this p forward and p backward. And so what happens is for the probability from the new thing, you have a p forward of the new trajectory and a p backward of the new trajectory, which will cancel these out. And from the old, you cancel these out. So that, because of microscopic reversibility, that cancels. And we're left with this. We just have the ratio of the of the probabilities of the shooting points, and then the ratio of the probabilities of the or the ratios of the indicator functions. So first off, if the modification we did was, say, without changing the total energy, which we'll just, for now, that's what the original algorithms were. They don't change the total energy at the shooting point. So the shooting point before and after modification, which are what those two things in the row are the same, have the same probabilities row. We get rid of that. And then we're also going to just get rid of these indicator functions. Can somebody tell me why I can get rid of the denominator indicator functions? What do I know about my initial trajectory? It was already part of the ensemble, so it had to start in A and end in B. So the initial trajectory started in A and ended in B. Therefore, that was 1. That thing on the bottom is just 1. All of this brings us down to a lot of ugly math that leads to a very simple expression, which is usually a sign of some fun science, in my opinion. But all you need to do is any trajectory that you create according to these rules that starts in A and ends in B, that trajectory is accepted. Any other trajectory is rejected. So if I start with a trajectory like that, and I create a new one like this, good, I can accept that. If I create one like this afterward, that's out. That one is not accepted. So, okay, what assumptions did we make in this? We said we had a symmetric distribution-preserving modification of the shooting point. We said that we are using reversible and distribution-preserving, or therefore distribution-preserving dynamics. We used a constant number of frames in each trajectory and an equal probability of selecting each as a shooting point. You can break these assumptions, but your acceptance probability will change. And in fact, I'll show you some of that, and we use those in some broken versions of that and with more complicated acceptance probabilities in practice. So now let's talk more about how to modify the shooting point. The issue here, this is the same with any Monte Carlo. You want an acceptance ratio that's on the usually 30 to 50% rate. If you make too small of a modification, then you may not see much of a significant change in that. And you get the same trajectory back every time. That doesn't give you much information. If it's too big, then you're going to reject it every time. And if it's rejecting every time, then you're not adding any information at all. So you have to tune that parameter if you're doing that kind of shooting, at least. But maybe there's another way around that. So if you're dealing with biomolecules, if you're dealing with large condensed phase systems, the velocity gets pretty much randomized in a relatively short period of time. And in the systems that I'm usually looking at, we're looking at the time for the trajectory from when it leaves the state to enters the other one, maybe 10 nanoseconds or 5 to 10 nanoseconds. And if the velocity is completely forgotten on a 1 to 10 picosecond time scale, then basically between each snapshot, I might as well be randomizing my velocities, already completely randomizing them. So the velocity actually doesn't matter that much in those sorts of systems. So let's just do an experiment, a thought experiment here. Let's start with the shooting point that's at the transition state. The transition state, you have a 50% chance of ending in A, 50% chance of ending in B. This is the optimal place to shoot from. So if I shoot from there, I'm going to go forward, so I need to end in B. Got a 50% chance that it happens. Got it. Now I'm going to go backward. Need to end in A. Got a 50, oh, that didn't work. 50% chance it happened, but it went to B instead. And in fact, this means that the best acceptance I can hope for in this kind of situation where velocities get pretty much randomized, the best acceptance I can hope for is going to be 25%. I'd like to have 30 to 50, right? Is there a way I can only shoot one way at a time? Well, if I do that, then if I change the trajectory and then shoot forward, then I have this non-physical change in the dynamics in the middle of it. And so that trajectory isn't even a real trajectory. It wouldn't exist. That's not acceptable. However, if I use a stochastic integrator, let's say like a Langevin integrator, something that uses randomness in order to, as part of the integration process, then I can shoot in only one direction because that's still a physical trajectory. I make no change at all at the shooting point. The change I made at the shooting point is that I have a different random number in my random number generator. And so that is something I can allow. This is what we do. So you select the shooting point. You randomly pick whether you're going to go forward or backward. I'll go forward. There you go. Now you have a trajectory that is a new trajectory, but some of the frames are still the same. That back part hasn't changed yet. So you don't want to keep doing the same thing every time, but you go again, right? I select a shooting point. I randomly decide whether I'm going to go forward or backward. This time I'll go backward. There we have it. We have a trajectory now that has no frames in common with the initial trajectory. We refer to these as, in one-way shooting, we refer to these as decorrelated trajectories. That does not mean that they are fully decorrelated in the sense that they're far from each other in space. It means that they have no frames in common, which is sort of a minimal decorrelation. Well, that's because I got to choose the dynamics in this particular case. In practice, yes, you will not get this good of acceptance. It depends. Actually, you optimize the acceptance based on how you select your shooting points, usually. I mean, that's because it's because I made the slides. Yes, I cheated completely to make that.
If you had not done that, if you make the chance,
then
go someplace and then you just take the other half.
My probability of going from here, my probability of having a forward shot from here accepted is exactly the committer at this point. And so if I'm really close to the state where the committer is very low, I will have a low acceptance probability. If I'm very close to the other state, then I'll have a high acceptance probability. But that's, so for the forward, it's exactly the committer. For the reverse, it's 1 minus the committer. But yeah. In fact, we use that connection to the committer is in fact used in some of the analysis that we create, which I'll come back to later. Yep. If the dynamics are chaotic, which is usually where we are in this case, right? The velocity is completely randomized anyway after 10 picoseconds or 5 picoseconds or 1 picosecond, depending on how you want to define fully randomized. So the velocity you started with doesn't matter. It's essentially so one of the ways to think about what we're doing here, because I should also say, this is as we often do in MD, we don't save every single time step. So like I said, this is going to be 10 nanoseconds with femtosecond time steps, and I'm probably saving every few picoseconds or something like that, maybe even longer between saves. So each snapshot represents a bunch of small MD steps that are actually taken. As a result, what we are effectively doing is we use MD we have a time step between steps that are basically like an overdamped Langevin or a Brownian motion type approach, right? But we're using a lot of tiny little time steps to actually calculate the move that's done in that overdamped picture.
Let's talk about a real example. So we have a protein and interval.
Mm-hmm. So
you find this path that the protein has followed, and it's very short. Now what you do?
How short is your path for the okay, yeah.
Yep. Okay, so now we go to the trajectory that's somewhere in the middle of the folding, right?
So no, we have, if it's a 5 nanosecond thing, that is from where it's folded to where it's not folded. Right. It's that time. You pick something that's in the middle of that, right, and you just integrate forward. Now there's enough randomness there that a Langevin integrator will certainly be reasonable on that time scale and will create spreads. Yeah.
If the velocities are randomized anyway, so they do not impact this event that much. So what's exactly driving this?
So again, the picture here is that what we would love to do would be able to just go directly in steps of of 5 picoseconds or whatever our save frequency is. But that we cannot do. We don't have an ability to create something that still has knowledge about the underlying dynamics so that we can do things like rates while also creating a step that's that big in time. So we use lots of little tiny time steps to generate that. We would rather have something that would just directly integrate with bigger time steps. That would be even better. But that's the physics make that impossible.
But I think that okay, so we're trying to see how this protein folds. Okay, we would find just one configuration that folds. Maybe there are others, but since we're always using the midpoint,
It's not the midpoint. It's something during that transition. And
since we're only using something during that particular,
you're concerned that there are multiple channels.
right?
I'll come back to that later. All right. The idea, though, so back to one-way shooting, there's no modification in the selected snapshot. That means we don't have to worry about this, how big to make our modification problem. That's a nice advantage. Now, how to select the shooting point. There are a bunch of ways of doing that. What I showed you already is what we call uniform shooting point selection, where you just give them all the same probability. There's another algorithm. I'm going to go through a few of these. This is where I've got a bunch of math that's kind of boring, but more boring than the other math. But the point is that every time you do this, you go through essentially the same process. So aimless shooting is a method. I really should put the citation on it. Peters and Trout, JCP 2008. Baron Peters and I can't remember Trout's first name. But, anyway, the aimless shooting algorithm, what they do is they take the trajectory and they look at 3 points. One is the exact midpoint, and then there's 2 that are on either side of it by some delta. And you select one of those to be your shooting point. Then you decide, you randomize velocities, fully randomize the velocities, draw from the Boltzmann distribution. Then you decide whether that new shooting point is going to be the middle or the sort of left or right side of that in the new trajectory. And you create the new trajectory from that. What this does is, because you're more likely to accept things that are near the transition state when you do this, right? That's what that little thought experiment we did. We get the best acceptance at the transition state when you have 50% chance on each side. What this will do is you'll basically like inchworm up towards the transition state so that eventually your shooting points are actually at the transition state. And yeah, you can continue doing this for more trajectories. So that's the idea behind aimless shooting. It's a very clever trick, and there are other things that have been developed since that I think are even better for that. Mathematically, this is sort of just the details on it. You have to think about how to split up the algorithm, just like I said, every time you do this. So you have a 1/3 selection probability for each of the shooting points, because each one, there are 3 you can select from. You have a symmetric modification probability, and you have a 1/3 of whether it'll be the first, second, or third in the new trajectory. And then you have the forward-backward dynamics, just as we did before. The result is that when you plug this in, you get the exact same acceptance probability. It's just dependent on HA and HB, even though you got to it through a different algorithm. Now, that's not always going to be the case. Sometimes you'll get a different acceptance probability, but sometimes you get the same one. You just have to work this math out. One thing that we use very frequently in our stuff is what's called flexible length shooting. So the idea here is that if your states are defined pretty well, correctly, I would say, once you enter that state, it should be very unlikely that you revisit the first state before coming back to the one that you, let's see, say that correctly. Once you enter B, it should be very unlikely that you revisit A before visiting B again. So if you exit B, you're more likely to come back to B than to go to A. This is the definition of a rare event. The probability is very low that you spontaneously make the transition. So if your states are defined as such, we don't need to spend all this extra dynamics in the state. We're just going to focus on from right when we leave the state till right when we enter the other one. And the reason we do that is because, well, that area will have a distribution of lengths, and this is a real example. In fact, this is probably a rather minimal case for where it's a problem. This is an alanine dipeptide. And you see that there's a distribution of path lengths. The average path length is much less than the sort of maximum that you need to go to. And in this case, I would say that you probably do about 5 times more dynamics if you do a fixed path length with the algorithm that we showed before with the fixed length. than if you use this flexible length approach. So the advantage here is you get much shorter trajectories. The disadvantage is that you need to stop the trajectory as soon as it enters a state. So your program needs to be monitoring the MD while it's running. A lot of MD codes, most MD codes, do not exactly make that trivial, and that is where packages like mine, OpenPathSampling, can be of use to the rest of the world. That's what we do, is we work on that monitoring stuff. Algorithmically, how do we do this? Again, we're going to split it into the parts, select the shooting point from the initial trajectory, modify the velocities, or we can use one-way shooting, and run forward and backward. So we get a very similar kind of setup as we've had before. The only difference, in fact, here compared to everything else is that the selection probability has changed. So we're looking here at a case where we have everything comes down to then just this ratio of these two shooting point selections from the new trajectory and the old trajectory. The difference is now we have different lengths. So the new length, the new trajectory has a length n, ln, and so the probability of selecting a point from that, if we use uniform selection, is 1 divided by ln minus 1, and the old one is 1 divided by lo minus 1. And so the probabilities then are lo minus 1 over ln minus 1. So this is a slight modification, and like I said, this is what we actually use for the most part in practice, because it's much more efficient.
If you divide the time steps
Mhm.
you put in between the opportunities, this ratio wouldn't change. However, you increase your resolution.
We assume that you have a fixed time step. That's in general, you can get around that in, I think you can get around that, but you'll lose some of the dynamic stuff with it, I think. But we assume you have a fixed time step, because usually in MD you do. You just say I save every 5 picoseconds or something like that. This is so you don't subdivide the trajectory. You don't resample the subdivision of the trajectory. You just say I've got, if I have 10 nanoseconds, that may be 100 frames or something like that, or 200 frames or 500 frames, depending on what your time scale that you save is. And if it's half that many, then I have half as many frames. If it's half that time, it's half as many frames. That make sense?
Yeah, but when you change it a little, okay, you limit the time the new trajectory has to take to reach your
In this sort of thing, you stop as soon as you enter any state.
So it varies.
Yeah. So the length of the trajectory, because this is why we have to monitor it, is that the length of the trajectory will vary, and you stop as soon as you hit a state. That's the part we have to do. There is, in addition to that, we usually add an extra criterion that you should stop if you get to something really long, because maybe you didn't define a state that's in your system that you didn't know about, and rather than have your computer run for 3 weeks on something you can't use, we just say what's the maximum length that we think is feasible for the system. So another one of these shooting point selection algorithms, you can think of just adding a bias around it. So if you get really low acceptance, maybe you want to try and force it to shoot near the transition state. And so you just sort of, if you think you know roughly where the transition state is, you maybe put a Gaussian centered at the transition state according to some collective variable, and then you're just more likely to select points that are near that. Again, the math is always basically the same. Here, the selection probability just depends on this function that you're using to select from, and it's all the same story as the previous stuff. So
you make a decision where you want to go, A or B.
Yes.
And then you can fail.
Yes.
With 50% probability.
Mm-hmm.
And it begs the question if you also not take that decision and then just always, keep the other part of the trajectory.
Well, because so you would violate detailed balance in that condition. Yeah, you violate detailed balance because you kind of have to make the decision. There's things we've done that there are ways of getting 100% acceptance, but they're in TIS where you always have a where you can go to either A or B. But come back to that later. Yeah. So just to sort of summarize here, shooting algorithm is a Monte Carlo for sampling transition paths. That's the most important thing here. There are a lot of variants of it that can provide better sampling efficiency. So these are the ones I show because this is the course I give to master's students, and I have the materials there. But there are new things being developed all the time. T.S. von Erb's group has done a couple of things that are more relevant for TIS, which I'll talk about later. But these are methods that are better at creating trajectories that are more different from each other, better decorrelated. And also there's the spring shooting move, which was developed in part by Faden right there, which is it's a lot like aimless shooting in its purpose, in that it's trying to get you to the top of the barrier. But whereas aimless shooting kind of does this inchworm way of doing it, spring shooting is a faster way of getting you to the top of the barrier. It kind of acts like there's a spring if you're not near the transition state that's pushing you towards the transition state. So it's a more efficient, faster way of doing the same idea, though. And that's a fair description, you would say. That's yeah. You're. Yeah.
So it's usually the one-way shooting.
Yeah, it's a one-way shooting approach. Although you can't do aimless one-way, no. But yeah, so it's a one-way. Spring shooting is a one-way shooting approach that does this. So that's the algorithm. Now in practice, what do you have to do if you want to do transition path sampling? All you have to do are come up with definitions for your states. So that's straightforward. Provide an initial trajectory. That's easy, right? And then just sample long enough to converge. All of these are really easy. No, they're not. That's where we come to the practical challenges, which are exactly those things that you actually have to do. How do you define a state? Well, you're going to define it based on some geometric criterion. So this is something based on, is a specific frame of your trajectory in the state or not? You could use distances, you could use dihedral angles, you could use the number of atoms in a cluster within some clustering distance. So examples here are, I give maybe that certain hydrogen bonds are formed, which are defined in terms of a distance between two atoms. Or there are specific values of some dihedral angles that you're using, which is what we'll use in the example. What makes for a good state definition? So this is a slide I stole from Peter Bollhaus, and this is a lot of things that are bad definitions. And we're cheating here because we've sort of shown a rough picture of contours of the free energy surface here, of where we know where the free energy is. Of course, you don't know that in your real systems. So it's easy to show mistakes when you can make an easy picture. What's wrong with the first thing? Well, I've got state A is defined like this, state B is defined like this. There are points that are in both state A and state B. That's right out. This one here, the problem is that the basin for B is actually pretty big, as is the basin for A, and not exactly aligned with our state definitions. And so part of the basin of B is actually in our definition of A. And this may sound like it's a really stupid mistake, but this happens. Like this is in your state definitions, it can be hard to avoid this in a real like biomolecular system if you're dealing with soft matter. Down here we've got the basins fully wrapped by our states. That's good. You know, no basin is in the other state definition. But remember, we're dealing with rare events. And the definition of the rare event is that it has to be, once you're in the state, very unlikely that you go to the other state. And here we have one where we're close to basin B, but we're not really there yet. So we still have a large probability of going back to A. So this means that this basin, this state definition, it's too big to really give a good to be correct, because it doesn't have it's not a rare event to do the return. Yes, I mean, it doesn't even have to be necessarily the transition state. Usually you get, I mean, committers drop off pretty fast, but I mean, even if you had something that was a 10% or a 5% committer probability, it doesn't have to be 50%. If it's like it should be small, like, you know, depending on how big, how much confidence you want to have, but 1 in a million would be a good start. So the last one is what you want. And one thing to notice about this is we don't try to keep the entire basin inside the state. The idea is that once you've entered this basin, you'll hit the state. You'll hit the state definition. And there's no way that you can accidentally hit the state definition. This is the key idea. We want the states to be small. So that is a good state definition. What about multiple states? Because I said my trajectories were going to be 10 nanoseconds long. Maybe there's more than 2 ways that I can get trapped for more than 10 nanoseconds. If you know what the basins are in advance, you use multiple state transition path sampling, which is built into OPS. And if you don't know what the extra state is, this is still a problem. We've worked on ways of trying to handle that, but often it just means that you have to discover that by running your trajectories, seeing if anything is hitting that maximum length criterion that I mentioned before, and seeing if you're seeing a lot of that happening, then you've got another state in a basin. I mean, this happened. I had the master student, actually a project I'll talk about in detail in a little bit, got his TPS set up just right before Christmas break, and then went to Thailand for a month. And came home to find, well, he was checking his results because he was that kind of student. So he found out while he was on vacation that there was an extra state that we hadn't accounted for yet. So he got back and had to redo a month worth of simulation. Well, that's that's what you do. You want to find it in advance if you can. You need an initial trajectory. How do you get an initial trajectory? By hook or by crook. Any way you can is fine. Important idea here is that just like in Monte Carlo, you might start with configurational Monte Carlo. You could start a configurational Monte Carlo of water with the water on a grid. That's not a physically realistic system, but you let it evolve, you let it equilibrate, and then you get something that is physically realistic. Same thing with trajectories. You can start with a trajectory that isn't a physically real trajectory, and then you let it equilibrate until it is one. So, yep.
Can I ask a bit of a provocative question that, I have been asked also the same question. So, what if your initial trajectory is, for example, from a very high temperature, has sampled a very distant fire than the more relevant one of the low temperature? So does your method be correlated?
That's also the question about multiple channels, and that's the next slide. One option is for, if you have access to it, to just start from a long simulation. Now, if your event happens once per microsecond, you can probably do that. Otherwise, maybe if you're Vijay Pandey and have access to folding at home data, or if you're David Shaw and have Anton. First off, do people know folding at home? Do people know Anton? There's not everyone. Okay, so folding at home, Vijay Pandey is a professor at Stanford, and if you want lots and lots of MD, you've got to have some trick to get that to happen. And Vijay's clever trick was that he created a screensaver that people around the world download and use their GPUs on their own computers to create data for him. And so this is a huge project where, and in fact, it's not just Vijay's group. Other groups use the folding at home infrastructure as well. But this is a huge way of getting lots of data. And yeah, people are very generous to donate their computer time. They leave their computers on overnight and they run simulations for them. Anton is a project from D.E. Shaw Research. And so David Shaw was a professor of computational biology originally, but then he went and worked for, I think it was Merrill Lynch, one of the big stock firms, and as one of the very early quantitative investors, got really good at it in about 2 years, decided he was good enough to go out on his own and started a hedge fund. That hedge fund, he started out with $28 million of capital in the late 80s, and when I was working with Shaw in the 2008, 20 years later, it was $28 billion. So yeah, that's a nice improvement. When you've got that much money, his personal wealth he's on Forbes, so you'll see that his personal wealth is like 2-point-something billion. So he started a little research group of his own, that about 100 people. That little research group. that they build special purpose computers designed to do molecular dynamics that are very, very fast. And so when the first Anton came out in 2008, it was 30 times faster than anything that was available before. The record for the longest simulation of a certain size of protein, BPTI was the protein they were doing, they did that was compared to 3-month simulations that had been done before that. They did it over a long weekend. It was Thanksgiving weekend, 2008. So yeah, it was fast. If you can do that, you can create millisecond simulations. That's what they're doing now with Anton 2 or 3 now. It's an interesting question because I think that GPUs are catching up to them. They're still faster because the HTIS unit is so fast at calculating distances. It's just customized to calculate distances between particles. I believe it is so fast that rather than usually when you calculate distances between particles, you loop I over I and then j greater than I or something like that. So you only do the half the matrix. Yeah, they just throw them all in there and just throw out half because it's that fast. But it's custom hardware that makes it possible. Well, it depends on how much money you have and on what you're trying to do, because they also they have like Leonard-Jones potentials in hardware. That's the other part of it, that all of those sorts of things are tabulated, and then it can be a lot faster that way. Anyway, that's the best way to get a trajectory, is to have either a lot of money or a lot of people working for you, or both. For the rest of us, we have to find some other clever way to deal with it. And high temperature dynamics is one approach. Metadynamics, which Gareth will talk about tomorrow, is another. Metadynamics is sort of where I prefer right now. What they do in metadynamics is they sort of fill in the wells. They change the underlying potential energy surface so that your stable states get filled up until you pop over to the other state. What that means is that, from my perspective, is that the dynamics in the well is completely wrong, but the dynamics near the barrier as of the first transition have not been perturbed, and that's probably still a good initial trajectory. So that's what we will. That's what I like to use. Other bias dynamics methods, if you want, you can use steered MD or whatever you like. It works just fine. Now the multiple channels question. How do you know that you are sampling the important channel and that you're not stuck in some channel that isn't as relevant? So in principle, this is a difficult problem. I'll talk about replica exchange TIS later, and that's something that can help it a lot if you can do that. In practice, in my experience, we've seen a lot of switching between channels in biomolecular simulations. I'll actually highlight that when I give the example later on. So that means that it's not necessarily as much of a problem as we fear. There's actually some interesting ideas about how to study this more directly, which I probably should have mentioned to Ralph, that I have a proposal in with Peter to do something on that, because that's with Peter and Jocelyn Freda, because we have an idea of a way to do that. But this is also still active research, really figuring these details out of how to get to the right channel and make sure you're not in the wrong one. Christoph also has a nice method, I believe. There's some sort of metadynamics plus TPS thing that I think is focused on that, but Andy doesn't seem to remember exactly what I'm talking about. So Christoph Delago published something on that a couple of years ago. Meta TPS, I think it was called. All right, so those are the practical challenges you have to face. It's not all trivial. I mean, there is still setting up these simulations. What do we learn from it? One of the most important things are what we call path densities. So this is an example from a project that I did where DNA basically, Watson-Crick, it can flip over the other way like this, and that's called Hochstein. So one of the base pairs just sort of rolls over. The question we had was, does it just roll over like this, or does it go outside and then come back in? And so what we have here on the x-axis is the sort of a measure of how close it is to Watson-Crick or the Hochstein state. And on the y-axis, we have a measure of how far it has opened out. So the further down it is, the more opened out it is. And it looks a lot like a free energy plot. It is a lot like a free energy plot, but it's normalized a little bit differently so that the emphasis is on the transitions instead of on just the areas where the trajectory stayed. It's supposed to highlight both the barrier region, if you have a narrow barrier, equally to the anything that's somewhat metastable within this. So that's a difference with a free energy. As an example, I mean, here I've got a couple of representative trajectories plotted, and you can watch the movies, and you can see it goes out, and it kind of wiggles around a little bit. And so here we're not fully out, but we're not just rolling over on the inside. We move to the outside a little bit, and eventually it'll flip over. There, it's pretty much flipped over, and waiting for those hydrogen bonds to form so that I'm in my state. There we go. And so that's an example of what we've got. So part of what we do in path densities is we like to interpolate over the frames that may have been skipped. So this is a two-dimensional histogram, of course, and you don't just look at where you went. You like to see where you went through. That will help you highlight the bottleneck barrier regions. And the performance, as you will see when you do your example of this later this afternoon, the performance right now for that is not great. So there are maybe ways to improve the performance of that, and that's one of the modules that I would suggest if you are interested in working on OPS, you might do. Another thing you might do with the results of a transition path sampling simulation is to run a committor simulation. So we talked about the committor. It's the probability that a trajectory initiated at some point, if you randomize the velocities, ends in state B instead of state A. And of course, this is particularly interesting because the committor 1/2 is the transition state, or more correctly, the transition state ensemble. Many different frames are at committor 1/2, and so many configurations are committor 1/2. So the set of all of them is the transition state ensemble, and that's how you help define your transition state. If you're trying to define your transition state, let's say that you looked at your transition state ensemble and you say, I noticed that all of these have some value q star of a potential reaction coordinate q in common. How do I know if q star is my transition state? Well, the committor 1/2 and the transition state are identical. It's the same thing. So here's that case. Q star is, all of the committor 1/2 frames are around q star. Does that mean I found my transition state? What I've said so far is that committor 1/2 implies my proposed transition state. So no, that's not enough. This is something that's often done incorrectly in the literature, so this is why I like to emphasize this. So I've only proven one arrow. I need to prove the arrow going the other way. I need to say that everything where q is equal to q star is also close to a committor of 1/2. And so that gives me the other arrow there. This is the same idea here. This is from Baron Peters. This, by the way, if you're interested in doing stuff with the committor, the citation at the bottom there is a great review article to read about this stuff. And the reason that you can go wrong here is what you see in the top picture. Here, this Q double dagger 1, I think this is my transition state up like this. But the problem is that I don't have a bunch of points with committor 1/2. Instead, I have a bunch of points with committor 0 and a bunch of points with committor 1. So that's where you want to be careful in your definition. And here's the correct thing. And he talks about what all these things are, but you'll get a distribution like this if it's wrong, one like that if it's right. You can tell that it's wrong because he puts a frowny face and is right when he puts a smiley face. Yes, that's an Anurev Phys Chem. Love it. Other things that we look at when we're doing TPS. One of the things you want to do is make sure your simulation's working, right? You want to make sure your simulation is giving you reasonable results, that there's not something kind of stuck or going weird. Like, you would look at a trajectory of MD to make sure that your system's not like blowing up or something. So what do you look at for path sampling? One thing is the path tree. And so this is for one-way shooting. And you want to make sure that you have both forward shots, which are in red here, and backward shots, which are in green. In OPS, we changed that to red and blue because we had to remind some people about color blindness. People who built this before us kind of forgot that some people are colorblind. And so, yeah, you want to see that you have forward and backward shots, both accepted, similar frequency. You want to see decorrelated paths. That's again where you see a trajectory that has no frames in common with the one before. So if I start from the initial trajectory, which is black here, this little segment of it stays the same all the way until there. And that's when it finally becomes decorrelated. In OPS, we also make it very easy to identify decorrelated paths. It's shown on the path tree. Another interesting thing you can do is to look at this least changed path, and yep, sure. These were, yes. It doesn't have to be that strong, but it means, so this is saying that, let's go back to the, without that. I mean, each one of these lines represents a trial trajectory that was generated. And so this is a forward trajectory. It was accepted, actually. These are only showing the accepted paths. And so this is a forward trajectory that was accepted. That trajectory, yes, used Lanzmann dynamics. Now, when I say it's decorrelated here, that doesn't mean that that doesn't mean decorrelated as much. It doesn't mean that if you could come up with some position correlation function or a trajectory correlation function that's 0. It means that it has no frames in common. This is our definition for one-way shooting of what decorrelation means. It's a minimal decorrelation. It's not a, I wouldn't say that means that it's fully sampled decorrelated. Because this is not decorrelated calculated from any sort of correlation function. There's no, it's kind of hard to define a correlation function for these things. So this is simulation time. So these are steps. This is just a frame number, basically. So I shot from this frame and went to there. I shot from this frame and went that way. So backward, forward, it's sort of a effective time of the simulation in a way. What do you mean it's the same thing? I didn't understand what you.
I mean, that thing was completely gone.
So this part of when I did this shot, all of this part of the trajectory got written over. Actually, when I did this one, after the first thing, the actual trajectory that's in the simulation is that. And then when it comes to this one, the actual trajectory in the simulation is that. Each one of these represents like there are boxes in here that represent snapshots from your trajectory. So this is at some point we had a trajectory that went like, actually, if I do it correctly, let's go for this trajectory. All right, so this one, the trajectory was these frames, and probably something there, something there, something there, and here, and I think I went to this. Yeah. The black one's the original. So you notice when I did that, I had to go back to the black one. And so at that point, I have not removed all frames from the black one. There's still frames in my simulation that came from the original trajectory. And that will be true. It's easy to you just trace down. It'll be true until there. Those frames stay until there. Does that make sense? It can. It depends on your simulation. It depends on your setup.
When do you know where to stop?
Good question. When statistics seem to be converging, right? You look at the statistics of the simulation, or you just run until you think you can't really afford to run any longer. That's also the case. You don't trust data if it doesn't have more than a few decorrelated trajectories. Now again, some of these other shooting moves, by focusing you near the transition state, you get more decorrelated trajectories in this sense. But then there's a question of, are you moving around, or you're just shooting from the same transition state all the time, right? So then maybe that part of the trajectory, it may be decorrelated in this sense, but it may always be near each other in phase space, which is not decorrelating. I mean, in this, the first path, and then this will be the first one that's decorrelated afterward, and so it goes to that. So you see that way, I never need to go back to the black one. And again, our code actually, in OPS, we draw little lines that mark where these are. You'll see that. So related to this is this idea of the least changed path, which is essentially trying to get you through this with making the least frames. It's not exactly the way it's defined, but the big idea of it is that it stays near the top of the barrier. And so it's a rough estimate to your transition state ensemble without actually needing to do the super expensive committer calculation. You get this basically for free. It's a very cheap analysis that gives you an estimate of your transition state ensemble without actually doing the committer simulation afterward. Another thing that we're interested in, we want to know what the reaction coordinate is, right? That's kind of the point of this. The beauty of transition path sampling, the argument for it was always that you don't need to input a reaction coordinate. You just need the names of your state, the state definitions. Then you just let it go, and it should tell you about the simulation. So this also should actually have the same citation as the Aimless Shooting, because it's the same paper, Peters and Trout and JCP in 2008. But this is, the idea here is that you're going to do a likelihood maximization approach, and you pick some collected variables that you think might be interesting, and you throw them all in. You assume that the true reaction coordinate is going to be a linear combination of those, and you have to assume that the committer has a certain functional form, which you usually take this half plus half tan h. The reason that you take that is that, I mean, the committer probably does have that because it's going to drop off very rapidly, and based on Boltzmann. And then you just use this maximum likelihood approach to optimize the results, or optimize the linear combination. It should say optimize the alpha and obtain R, or alphas and obtain R. And this is just an example of that, where a helix and then some RMSD carbon alpha were what ended up being the most important reaction coordinates in this simulation. So now an example of TPS in use. So this is sort of the real scientific part. KROS is it's a GTPase. It's a protein that is involved in signaling networks, involved in cell differentiation, growth, and division. If you have too much cell differentiation, or too much cell growth and too much cell division, you get this thing called cancer. And ROS family mutations are present in 15% of cancers, human cancers. 85% of those are in KROS. So this is an important protein in cancer, and it's one that's been very difficult to target drugs to, because it has been hard to understand what's happening in the dynamics of it, and hard to understand why it's causing cancer in some cases. It's part of this whole overall structure of this whole cycle biologically, but what we're looking at is up here. So we have these two switch regions in green and in blue, switch 1 and switch 2, and there's this equilibrium between what's known as state 2, where they're kind of closed and more ordered, and that state 2 is active. And then there's also state 1, where they're floppy and disordered, and that is not active. So the hypothesis is that maybe a cancer-causing mutation shifts that equilibrium toward that state 2 so that it is active more. And so we wanted to look at the dynamics of GTP to look at that, or of KROS to look at that. We're looking specifically at the Q61L mutation, which is oncogenic. Residue 61 is part of switch 2. It's not a charged residue. It is changing a hydrophilic residue to hydrophobic. I need to change that slide. And this is oncogenic. It's actually more relevant in HROS, which is another variant of ROS, than it is in KROS. But actually, we think our results have more implications for HROS. Or our results are consistent with it being more relevant in HROS. Let's put it that way. We did TPS simulations using multiple state transition path sampling. Separate runs for switch 1 and switch 2. Each switch had 3 states. We did separate runs for the wild type and the mutant. That makes 4 total simulations. We're only going to bother with the results from switch 2, because that's where the interesting stuff happens. So the first thing we wanted to look at, well, the first thing I should do is to look at the protein itself. So this is what KROS looks like. It's bound to GTP. Down here we have switch 1. Up here we have switch 2, and here's our mutated residue. And then here is this alpha-3 helix, and that alpha-3 helix is going to turn out to be really important. In fact, that importance is one of our significant discoveries in this work. What are the states for switch 2? It can be bound to the GTP. It can be fully open and open to solvent, or it can be bound to this alpha-3 helix. That alpha-3 helix bound state was, I think, the one that my student had to redo his simulations because of. Also ends up being the really important one. Also was crystallized once, so we know it exists, but of the like hundreds of ROS crystal structures, it's in one of them. So it's not been focused on very much by people. When you're doing multiple state TPS, as we are doing here, you can switch between different channels. So I can start with, we're doing one-way shooting, I can start with a trajectory that goes from A to B. And if I do a forward shot, maybe that turns into a trajectory that goes from A to C. And then if I do a backward shot from there, maybe that turns into a trajectory that goes from B to C. So I can switch between these different transition types, and that's a way of switching between channels. First thing we want to know is how much does that switching happen, and is it different between these two, between the wild type and the mutant? It's pretty different. So here we have the wild type, there we have the mutant, we have our three states. We have arrows representing a transition from GTP to open, then I have these curved arrows. So this one says I switched from a GTP to open to a GTP to alpha-3, right? So that's what this one says. This one switches the other way. And so we have all of this switching here. The big thing to notice is that there's a lot of switching here. There's no switching there, or not much. Yep. That's just how it's illustrated. The thickness of the arrow is the number of switches. So that's no. This is a just schematic of the number of switches from here to here, and it's thicker because there are more of them. Here it's thinner because it just and why are those? That's just the order in which they were plotted. That's. Yeah, no, there's nothing that breaks detailed balance in this because this is all from a single simulation, so it has to move through these things. They don't. Yes, you're saying that you would expect these to. No, they're not. Let's see. I think the number of switches is related to the rate of how much you would see between these, which is going to be related also to the depth of each channel. So it could be that one channel is more probable than the other. And because there's three of them instead of just two. Let's see. I think if you only had two, it would have to be symmetric. But I think if you have, because we can do all of the switching, because what can happen is, if this is really more probable than either this, if this is more probable than the other two channels, then you'd see more switching into that than away from it. But again, this. Well, no, this is a 6 state because we have 6 transitions in that. Because this is also sort of the next stage of what we're interested in doing is the path sampling, or is rare events in rare events, and that's what we're getting at now. Yeah, I think this is going to go. This goes a little bit far out, I think, at this point. But the point is that we saw that there was a lot of switching. This tells us that there is something fundamentally different in the dynamics between the wild type and the mutant. So we wanted to investigate that further. What is going on that's different here? Now we use one of these path density plots. And this is for going from GTP bound to open, so it's to the full opening thing, not including this alpha-3 helix thing, just the full opening. And we see that, so this is a measure of how close the switch 2 is to the GTP. So that's kind of how open it is. So this is moving towards being, this is bound, this is open. And this is how close switch 2 is to the alpha-3 helix. And so that's moving. So what we see is there's a channel here in the wild type where the switching happens far away from the alpha 3 helix. And there's also some where it happens close, but the predominant thing is when it's far away. In the mutant, it only happens when it's close. And what does that mean? Well, let's look at the protein again. For it to open up, for the switch to open up when it's far away from the alpha 3 helix, that means it's opening just to direct solvation. It's just directly solvating. And when it's staying close to the alpha 3 helix, it's not directly. It stays close to something that's hydrophobic, and it's not fully solvating. In fact, we think that that it wasn't a fully solvated thing anyway, that it's getting stuck, still attached to the protein. So what this means is that because we've replaced this hydrophilic residue with a hydrophobic residue, we lose that direct solvation channel. And because we lose that direct solvation channel, it stays closer to this closed and active state. And so this is what's happening. This is the problem. It stays active because we've switched a hydrophilic residue out for hydrophobic, so it doesn't open up and solvate as it would otherwise. So yes, this is sort of the statement of conclusion. The Q61L mutation makes direct solvation unlikely, leading to more time spent in the closed active 2 state. And that is what causes abnormal cell growth and proliferation. This is why it causes cancer. It's in switch 2. It's the one that's in. Yeah. So these kinds of problems. I mean, this is what I think is fun with this stuff. We take something that we started out with, we just put in the physics of our simulation, right? We just are running molecular dynamics, which is fundamentally about physics. And from that, we get something that we interpret in terms of understanding the difference that we've switched from something that's hydrophobic to hydrophilic, or hydrophilic to hydrophobic. So that's a chemical concept. And then that applies to the fundamental biology here, which is a question of why is this protein causing cancer? So this is a cool example of what you can do with these tools. Another thing that we've worked on a little bit is this unbinding of selective inhibitors from a kinase. The idea is to predict the residence time for this system. The reason we care about residence times is that basically, so this is a reversible inhibitor. A reversible inhibitor is working when it's attached to the drug, or when the drug's attached to the protein, and it's not working when it's not attached, but there's an equilibrium. So of course, you want it to be attached more than not. But that equilibrium is the ratio of an on rate and an off rate. Just from experiments and years of people looking into this, it turns out that the on rate almost never matters. The on rate stays about the same whether you change the drug, whether you change the protein, if you mutate a protein or change the drug in some way. But the off rate can vary by orders of magnitude. And so because of that, it's a predictor of the efficacy, is just to calculate the off rate. It's hard to capture experimentally, and so we need advanced simulation techniques. We're using TPS and TIS for that. TIS is transition interface sampling, which I will briefly go over now. TIS differs from TPS in that we have these interfaces. And now we have multiple path ensembles that we're sampling simultaneously. We have a state, another state, multiple ensembles. And the rule now, Path Ensemble has a rule. The transition Path Ensemble that we did before had to start in A and had to end in B. This one, it has to start in A, it has to cross the interface, and then it can either go back to A, like these do, or it can go on to B. Both of those are allowed. And we use TIS to calculate rates. The big idea here is that it's really hard to calculate something that has a 1 in a million probability. But it's really easy to calculate 6 things with a 1 in 10 probability, and to get that at a decent statistics. So what you do is you draw a line, and you say, okay, I want to look at all the paths. I only am looking at paths across this line. I'm only considering trajectories across this line. I'm going to require all of my sampling to be trajectories that cross that line. And I'm going to count how many of them cross the next line. And that's going to be a number somewhere on the scale of 1 in 10. Then I'm going to sample trajectories that have to cross this line, that must at least go this far. And then I'm going to say how many of them go to the next line. And that's again going to be 1 in 10. Of course, the probability, if the probability of getting the trajectory left here and got here is 1 in 10, and the probability that if it got here, it got to there is 1 in 10, then the probability of it going from here to there is 1 in 100. And so you keep doing this all the way across, and you get a very small number. Just to do the exact same thing, but with math this time, the rate is equal to the flux through the innermost interface times the probability of going to the first interface, so interface 1, assuming you crossed interface 0, times probability of going to interface 2, assuming you crossed interface 1. All the way across, you just get something that looks like this product here. In practice, we don't actually just calculate these products, and we don't calculate each of these terms in the product and multiply them together. There are algorithms that are histogram combining algorithms that are improvements on that. So we use an approach based on the weighted histogram analysis method, or WHAM. But there are also other approaches that have been developed, and that's another one of the modules that I suggested, is that you can use some of these alternate methods for calculating the total crossing probability and implement some of those. Within transition interface sampling, there's an improved version of it called replica exchange TIS. The idea is that we are sampling these paths, multiple of them. All of these are being sampled at the same time. The rule is, for the red path has to cross the red interface. The blue path has to cross the blue interface. But sometimes the red path will also cross the blue interface. That can happen. The blue path, of course, has to also cross the red because the red is further in than the blue. We can then do a replica exchange move where we can just switch which ensemble the paths are associated with. This is just like if you do replica exchange MD, you may switch which temperature a given configuration is associated with. We do the same thing here. We can just switch which path ensemble it's associated with. And so now down here, the path at the top is in the blue ensemble. It used to be in the red. And the path in the red for the red ensemble is the one on the bottom. The nice thing that this allows, we talked about channels a few times. Let's say that I had a big barrier here, and I had a channel that went around like this, another channel that went around like that, and I had a barrier here. This enables me to switch between those channels. And in fact, because I will sort of spontaneously sample that, you will eventually do that, and you'll do that much more quickly than you would with something just like straight TPS. Another thing that we use with this is what's called the minus move. I'll go through it relatively quickly. The big idea here is, again, it's all about decorrelation. You want to decorrelate within the state. So if you combine replica exchange, you also want to make sure that you've gone inside the state, because maybe you need to come out on the other side. So you take a trajectory, you run dynamics for a little while inside the state, and then you create another trajectory that has left the state. Our version is slightly different than the original version, but this is what we implement in OPS. And you're left with a new trajectory that has decorrelated in phase space, in configuration space, significantly. In practice, that makes a huge difference. So this is, for a very simple system, I came up with a measure of correlation between the paths, or between the paths is a fair way to say that. It's technically between the initial conditions of the trajectories. And when we include the minus move, it decorrelates much more quickly than if we do not. This is in wall time, because the minus move is in fact very expensive compared to a regular shooting move. It's a longer trajectory usually, but the decorrelation is faster in wall time. Another thing that you can look at with TIS is a reweighted path ensemble, which gives you a way to calculate a lot of properties, most importantly probably the free energy. So this is from some work on unfolding the trip cage protein, and you can get a free energy profile in any collective variables that you're interested in. That's the nice thing with TIS, is that these dynamics are unbiased. Therefore, you can use any of the variables, any variable you think of after the fact, to look at it as well. This also is something that I've suggested as a possible module that someone might want to do, is to add the reweighted path ensemble, because it's one of the only things in here that we don't already have in OPS. Pros and cons of TIS. Pros, you get rates, free energies, all of that, one simulation. TIS is very forgiving with respect to your choice of order parameter. You do need an order parameter to define these interfaces, but TIS is pretty forgiving in that if that's not correct. Umbrella sampling, for example, on the other hand, is not very forgiving. It's good if you're doing multiple channels, and there are methods to use it with multiple states as well. Disadvantage, you do have to have this order parameter, although that's pretty much true with all methods to calculate the rate. And it's expensive. These path sampling methods are not cheap. This will require thousands of small trajectories. Just overviewing the methods, transition path sampling, it's mainly focused on mechanisms, things like the reaction coordinates, stuff like that. Transition interface sampling, that also gives you access to rates, free energies, things like that. It's more expensive, but again, variants of both of these exist to study multiple state systems, which is important because that can save you a lot of time. So that is almost done now. We're just gonna go over OpenPathSampling as some background before taking a break. So what is OpenPathSampling? It is a Python library for path sampling simulations. The website is openpathsampling.org. We have a Twitter handle because I guess it's 2019 and that's now required. The development is on GitHub and it's open source. We encourage you to participate, and we participate in the Omnia consortium, which is also how you download that through the Omnia channel. Our goal has been to make this something that's easy to use so that people who are just getting started can use it. And also, it's very important to us it's easy to extend. I develop new methods. I want to be able to easily add these things into my code. It's independent of the underlying dynamics engine, which means that it can be useful to people from other fields. That's our goal, at least. So one of the things you'll notice, everything I said about path sampling, it's just about trajectories. It was never about molecules or atoms in any way. If you had, so you need to have this microscopic reversibility. But if you were simulating the stock market with microscopic reversibility, I don't think you can do that, but you could try and do path sampling on the stock market. There's nothing about the method that fixes it to being about molecular systems. And yeah, this is the there are 2 articles that came out this year on it back to back. I feel sorry for our poor reviewers who had 80 pages of review to read, but they did. So OpenPathSampling is a library. It's not exactly a program. A program makes it easy to do the most common tasks, so you can focus, and it focuses more on speed of setting something up rather than flexibility of being able to do whatever you want. Libraries are designed to be easy to extend, make it possible to do new things. A lot of my conversations with my co-author, Jan Hendrik, were about along the idea of, what if somebody wanted to do this, some crazy idea? And the other one says, well, why would anyone want to do that? And we're like, well, I don't know, but it's possible, right? And so we tried to make it possible for you to do something that maybe we hadn't planned on with our code. And of course, you can always wrap this into something that's a simpler package if you want to. Steps in path sampling. This is true no matter what. Now, when you do the examples today, you'll do these actual steps, but I want you to be sort of aware that these are the things we do, the order we do them. First thing you have to do is figure out, what are you going to study? What will you be simulating? How are you going to run the MD? Are you going to be using NVT dynamics, NVE dynamics, NPT? You need to make that decision before you start. Are you studying alanine dipeptide? Are you studying a cluster forming? You need to make those sorts of decisions. In OpenPathSampling, that goes into what we call the dynamics engine. You need to pick out some collective variables and order parameters that matter to you. What are the functions that you're going to use to define things in your system? So that'll be distances or dihedrals or things like that. These are what we call collective variables. Then you'll use those order parameters, or those collective variables, to define your states. And you have to say, how do you characterize your states? So for example, the collective variable might be a distance, but then the state also includes what range of values are allowed for that distance. And in OpenPathSampling, we call those volumes. You need to decide what reactions you're going to be studying and how you're going to study it. Are you using TPS? Are you using TIS? And that's what we call the network or transition network. Path sampling is Monte Carlo, so you have to decide what Monte Carlo moves you want to use. You certainly want to use a shooting move, but maybe you want to customize the shooting move. Maybe you also want to do replica exchange if you're doing replica exchange TIS. You need to decide how frequently you're going to do each kind of move. All of that is in the OPS move scheme. You need initial conditions. And so that's in a data object that is called a sample set because it can have more than one set of initial conditions in it. You're going to save your results somewhere, because why would you spend so much time on the computer if you can't analyze it afterward? So we put that in what we call storage, and then you put it all together into the actual simulation that you're going to run. And we call that the path simulator. The whole structure is a little bit more complicated, and you can see these arrows sort of show the inputs of each thing to the other. By the way, this figure is in the paper, so if you get the OPS paper, this figure is in there. So let's talk tutorial. The tutorial is at that URL. The idea is that you will run a short TPS simulation. You'll set it up and run it yourself. You'll do some simple analysis on that TPS simulation. Then you'll do some more complicated analysis using a pre-calculated simulation. It's the old cooking trick. Like if you ever watch cooking shows, right? They put it in the oven, and then they come back from commercial break and pull out the fully baked cake, right? So we're going to do the same thing. I've got the fully baked cake online, so you can just download it. And finally, we'll also do some analysis on a pre-calculated committer simulation. There's also an example of a multiple state TIS simulation that you can do if you want. These first four, excuse me, are with the assumption that you actually have to do work on it. You'll see things that say your turn. So for example, I define one of the collective variables, and then you have to define the other one. We're looking at allylated peptide. It's the Ramachandran angles. I think I define phi, and you define psi. Defining the states, I define the equatorial state. You define the alpha R state. It has instructions on what the values should be for that, but the trick is for you to actually do some of this along the way. And again, the modules that might be of interest: alternate approaches to the total crossing probability, reweighted path ensemble analysis, alternate interpolations for path densities. Also, not mentioned during the talk, but additional dynamics engines. We support any underlying engine in principle. And so if you are familiar with some other engine, or if there's something that's more related to your work that you would like to add support for with OPS, it should not be too hard in principle. The basis is just writing about 4 functions in Python, but there can be tricky bits if you need to deal with intricacies of how your code works. So yes, these are the summary points. I hope you got them. Path sampling is Monte Carlo in path space. If you didn't get that, then I really failed. Shooting move is the way we generate new trajectories. We can learn a lot about what happened during the transition from path sampling. TIS is the way we calculate rates and free energies, and OPS is a library that implements all of this. And of course, I'm very thankful to all of my various funders listed at the bottom and supporters from that. And I should have listed on here, Jan Hendrik Prince is my co-author who wrote half of the OPS code. Usually I put up a picture of him. Sander Root was the master's student, who's now a PhD student in Trondheim, who did all of the work on the KRAS stuff, and collaborations with Peter Bullhaus, Jostein Freyda, and a few other people. Thank you.